very happy to speak at this seminar. Yes, my title today is Hom-infinite Higgs categories, and this is based on ongoing joint work with Yilin Wu, who is presently at Hefei at the University of Science and Technology of China. And the plan is as follows. Well, the title is Hom-infinite Higgs categories, but I will not assume that you know about Hom-finite Higgs categories. So most of the talk will be a reminder on Hom-finite Higgs categories. And before that, I would like to start with a reminder on the AMYO cluster categories. Then I will come to another reminder on X-triangulated categories following Nakaoka and Palu, and then I will introduce Hom-finite Higgs categories. And in the third section, I will generalize to the Hom-infinite case. Okay, so let's start with the reminder on AMYO's cluster categories. We start from a finite quiver Q without loops and without 2 cycles. For example, we can take this 3 cycle, and we work over a field algebraically closed of characteristic 0. For concreteness, let us take the field of complex numbers, and we fix a potential on Q. That's just a possibly infinite linear combination of cycles. So here we can take the cycle A, B, C, and then associated with the quiver and the potential, we have the so-called Jacobian algebra. The Jacobian algebra, I will recall the definition a little later. It is the path algebra of this quiver. So here it is infinite dimensional, and then this path algebra, and then we impose relations which are deduced from the potential. Namely, we take for each arrow of the quiver, we take the so-called cyclic derivative of the potential, and this cyclic derivative is going to be a relation. So here we have the arrow A, and the associated cyclic derivative is BC, and so we have the relation BC in this Jacobian algebra. Yes. So for each arrow, we have a relation which closes the cycle in the potential. Okay, so here we get this very small, let's see, 6-dimensional algebra. And now, well, in general, it is easy to get infinite dimensional algebras, but now let us assume that the Jacobian algebra is finite dimensional. And then Claire AMYO in 2009 has constructed a triangulated category, the so-called generalized cluster category, CQW, which is Hom-finite and 2 Calabi-Yau. Yes, CY stands for Calabi-Yau. And triangulated, which moreover contains a special object, a distinguished object, a cluster tilting object, whose endomorphism algebra is isomorphic to the given Jacobian algebra. Okay, and let me quickly recall what a cluster tilting object is. So it's an object which is rigid, it has no self-extensions. And secondly, it is a generator of the category in a very strong sense. It's a 2-step generator. For every object, we can find a triangle whose cone is the given object. So you can think of this as a kind of presentation of the object X, yes, analogous to a projective presentation of a module. So here the TIs, of course, belong to the closure of T under finite direct sums and direct sums. Okay, so using T, we can resolve in a certain sense every object of our category in just 2 steps. Okay, and then a bit of terminology. The pair consisting of this triangulated category and the cluster tilting object is called a triangulated categorification of the quiver with potential. And well, the motivation and the terminology, yes, the word cluster, which appears here and here, this word cluster comes from the study of cluster algebras in the sense of forming Zelowinsky's fundamental 2002 paper. So the idea is that we would like to categorify cluster algebras. And well, I have no time to go into any details concerning this. Let me just say that why do we want a triangulated category? Yes, we want a triangulated category because the triangles in our category allow us to model or to lift to the categorical setting the so-called exchange relations in the cluster algebra, yes, which are of course fundamental. And but this, yes, so this link between triangles and exchange relations is a non-trivial one. Yes, so in particular, it has nothing to do with just with the Grothendieck group of this category. Sorry, I should K0 of the category C of the cluster category CQW. Usually, the Grothendieck group of the cluster category is small and uninteresting. Okay, so yes, so far. And then a third remark, yes. So here we work with such quivers without loops and 2 cycles, and then the cluster algebra, which is associated to such a quiver and categorified by the cluster category. This cluster algebra, by definition, does not have so-called frozen cluster variables, which are also called coefficients. However, the cluster algebras which appear in practice, in Lie theory and in geometry, they do have coefficients. Yes. And in order to get hold of the coefficients, well, we have to, instead of quivers, we have to consider so-called ice quivers. An ice quiver is just a quiver together with a frozen subquiver. And I'm sorry, I forgot to give you the link to the notes. Let me put it into the chat right now. Just a moment. Okay, so here you have the link to the notes so that you can go back if necessary.
So Bernhard, a question maybe. So,
Mm-hmm.
so the frozen subquiver is full, or?
It is not necessarily full. Yes, here we have an
you.
example from geometry where it is not full. Yes, so we have this frozen subquiver, and we also have this arrow, which is non-frozen. So it is in general not a full subquiver. Yes. Okay. And yes, so this ice quiver describes the so-called double Brüher cell for the group PGL4C. Well, it describes in the sense that the coordinate algebra of this double Brüher cell is isomorphic to the cluster algebra defined by this ice quiver. Yes, with the frozen vertices corresponding to the frozen cluster variables, to the coefficients. Mm-hmm. Okay, and now, well, for ice quivers, we have a corresponding version of the Jacobian algebra, the so-called relative Jacobian algebra. So we take an ice quiver, so the quiver together with its frozen subquiver, and a potential, which is just a potential on the quiver Q. And then we have an associated relative Jacobian algebra, which is the completed path algebra of the quiver, modulo all the relations obtained as cyclic derivatives with respect to non-frozen arrows. And we take the closure of the ideal which they generate. And then we also have the associated boundary algebra, well, which is associated with the idempotent given by the sum of the idempotents associated to the frozen vertices. Let's look at an example. Yes, here we take again the 3 cycle, but now these 2 vertices and the arrow linking them are frozen, and we take the same potential. What is the Jacobian algebra? Well, it is the path algebra, the completed path algebra of this 3 cycle, modulo the relations which come from cyclic derivatives with respect to non-frozen arrows. Okay, well, here we have a non-frozen arrow, and it yields this relation opposite to it. Here we have another non-frozen arrow, it yields this relation opposite to it. And well, this arrow is frozen, and therefore here we have no relation. Yes, these are just 0 relations of these 2 compositions vanish. And what is the boundary algebra? Well, we have to look at the subalgebra given by the frozen vertices. Well, so we have these 2 vertices, then we have this blue arrow, and then we have the composition of these 2 arrows, which goes in the other direction and which also yields an element in the boundary algebra. So we have these 2, and as you can see, if we compose them in this direction, then we get 0 because already this composition vanishes, and if we compose in this direction, we also get 0 because already this composition vanishes. So we get, as our boundary algebra, we simply get the pre-projective algebra of type A2. Okay. And now we would like to use we would like to use Frobenius categories to categorify ice quivers with potential. So what should that be? So we take an ice quiver with potential, and then instead of looking at a triangulated category, we look at a Frobenius category. So an exact category in the sense of Quillen with enough projectives and enough injectives, and where these 2 classes coincide. And we assume that the associated stable category, the quotient, the additive quotient by the ideal of morphisms factoring through projectives, is Hom-finite and 2 Calabi-Yau. It's a triangulated category. So we have such a Frobenius category, and we have a cluster tilting object. Yes, the definition is the same. We just have to replace the triangle with a conflation, an admissible short exact sequence in this Frobenius category. And now, well, since we are in this Frobenius category, we can decompose our cluster tilting object into a maximal projective summand plus a rest. And this maximal projective summand, yes, it should correspond to the frozen part. And this is made precise by requiring that we should have an isomorphism between the endomorphism algebra and the Jacobian algebra in such a way that the endomorphism algebra of P, which sits inside here, corresponds exactly to the boundary algebra, yes, to this the algebra associated with the frozen idempotent. Okay, now just the fine print. I assume that my Frobenius category is Kohl-Schmidt, so we have well-defined decompositions of our objects into finitely many indecomposables with local endomorphism algebras. It's Kohl-Schmidt, but it may be Hom-infinite. However, this associated stable category should be Hom-finite, and so that it makes sense to speak about the 2 Calabi-Yau property, yes, which says that the dual of the space of morphisms from X to Y canonically identifies with the space of morphisms from Y to the second suspension of X. Okay, let's look at, well, so let me look at two theorems which give us certain Frobenius categorifications. So first of all, a kind of meta theorem due to Geis-Leclerc and Schröer in a long series of articles. They show that large classes of ice quivers with suitable potentials which appear in Lie theory admit Hom-finite Frobenius categorifications. And on the other hand, we have an example, a nice class of Hom-infinite Frobenius categorifications due to Jensen, King, Su. They have introduced such categorifications for the ice quivers associated with the Grassmannians and also more generally with so-called positroid varieties inside the Grassmannians. So here we have examples. So here on the left, we have the example 0 from the theory of Geis-Leclerc-Schröer. Yes, it is this ice quiver, which describes the subgroup of this maximal unipotent subgroup inside the semisimple group of 3 by 3 matrices with determinant 1. Yes, well, as a variety, this is not very interesting. Yes, it is just affine 3 space, but it has an interesting and important cluster structure, which is encoded by this ice quiver. And then the corresponding Frobenius category is simply the category of finite dimensional modules over the pre-projective algebra of type A2, which we have already encountered as boundary algebra. And of course, it is finite. On the other hand, here we have the ice quiver, which describes the Grassmannian of planes in 4-dimensional space. Yes, to be quite precise, it's the cone of the Grassmannian, the Plücker cone. And well, as you can see, it is a slightly bigger, and the corresponding categorification is given by the category of Cohen-Macaulay modules over the associated boundary algebra. Yeah, the potential is the natural one, yes, the alternating sum of the triangles. And then you have a well-defined boundary algebra. It is an algebra of infinite global dimension. You can look at the Cohen-Macaulay modules over this algebra, and they yield a Hom-infinite Frobenius categorification of this ice quiver with potential. Okay, so we see that many ice quivers, many interesting and important ice quivers do admit Frobenius categorifications, but there are also many and even very simple ones which do not admit Frobenius categorifications. So, for example, we can look at this very simple quiver. This quiver does not admit a Frobenius categorification. Why not? Well, assume that we have a Frobenius categorification. So we have our Frobenius category E together with the cluster tilting object, which will have two indecomposable summons, a projective one, which corresponds to the frozen vertex, and a non-projective one corresponding to the non-frozen vertex. And well, if we're in a Frobenius category, then I claim that necessarily the space of morphisms from T2 to P1, so from T2 to P1, so in this direction, this morphism space has to be non-zero. On the other hand, well, since we only have this unique arrow going from left to right, it has to be zero, yes, if we look at the endomorphism algebra. So why is it non-zero? Well, you can easily check from the definition of the cluster tilting object that in such a Frobenius category, necessarily the full subcategory of projective injective objects simply consists of the finite direct sums of this object P1. And well, we know that in a Frobenius category, by definition, every object admits an inflation into an injective object, and in particular a non-zero morphism to a finite direct sum of such copies of P1. And so necessarily Hom T1 P1 is non-zero. Yes. Okay, so there cannot exist a Frobenius categorification of this ice quiver. And now the aim is, well, we cannot have a Frobenius categorification with a Quillen exact Frobenius category, but the claim is that if we use the more general X triangulated categories in the sense of Nakaoka-Palu, then we can find a Frobenius X triangulated category instead of a Frobenius exact category, which yields a categorification. Okay, so let me now recall what an X triangulated category is. Okay, well, first of all, the philosophy is the following one. Yes, we have the notion of exact category, and this notion axiomatizes the class of extension closed subcategories of abelian categories. Yes, every small exact category is identifies with an extension closed subcategory of an abelian category. And in a similar way, the notion of the X triangulated category is meant to categorify, to axiomatize the notion of extension closed subcategory of triangulated categories. Yes, so this is the motivation. And now a brief sketch of the definition due to Nakaoka and Palu from 2019. So what is an X triangulated category? It is an additive category together with a bi-additive bi-functor. So you should think of the X1 functor, which we have in an exact category or in a triangulated category. And well, when we have an element of such an X functor, we can associate with it a conflation in an exact category. And here we assume that we are given a map which takes each element of the bifunctor to a three-term complex, yes, with n terms X and Z. So in it, exact categories are particular examples, and then we can take the usual X1 of the exact category and the usual map taking an element of X1 to the corresponding three-term complex. And of course, this three-term complex is not completely well-defined. It is well-defined up to equivalence, where equivalence is a morphism which induces the identity in the left and the right hand terms. Okay, yes, so what we have is a class of three-term complexes which is parametrized. It's parametrized by this bifunctor. Yes. So in the case of an exact category, one usually constructs this bifunctor from the class of exact sequences, and one can do that in triangulated categories as well. But here we go in the other direction. We give ourselves the bifunctor with the realization from the outset. So we don't look at a class of sequences, but at a parametrized class of sequences. Okay, and a bit of notation. Yes, when we have a three-term complex which realizes a given element of the bifunctor, we write a diagram like this, and we have the usual terminology. The morphisms I are called inflations, the morphisms P deflations. The whole thing is called an X triangle or a conflation. Okay, yes. So if we were in a triangulated category, then here we would write sigma of X, but we are in an X triangulated category, so there is no suspension functor. So this is just a symbol. Okay, and now using this notion of X triangulated category, it generalizes both the notion of exact category and the notion of triangulated category, and more generally, it axiomatizes extension closed subcategories of triangulated categories. And now we can use the generalization machine and easily generalize standard notions which we have in exact categories to extra-angulated categories. So for example, we have the straightforward generalization of the notions of projective object, of injective object, of having enough projectives or injectives, or of being a Frobenius categories. Yes, this all this generalizes in the obvious way. And then, well, if we have an exact category, then it is in particular an extra-angulated category, and if it is Frobenius exact, then it is also Frobenius extra-angulated. And there are certain nice constructions which we can perform on extra-angulated categories and still get an extra-angulated category. So if we take an extra-angulated class category and any class of projective injective objects, then the additive quotient of our category by the ideal of morphisms factoring through an object in the class is still extra-angulated. Okay, so this is a useful way of producing new extra-angulated categories from old ones. And in particular, if we have a Frobenius extra-angulated category, well, then we can form the associated stable category. And this stable category is actually not just extra-angulated, but triangulated, yes, which generalizes Hupple's theorem for exact Frobenius categories. Okay, and then we can further generalize in an easy way. Yes, so when we have a Frobenius extra-angulated category, then we have the associated stable category, which is just a usual triangulated category. So we have a notion of being stably two Calabi-Yau, and we have a notion of cluster tilting object, yes, which you can just copy the definition and substitute the corresponding notions. Okay, and now let me show you that this ice quiver does admit a Frobenius extra-angulated categorification. Okay, and well, we will use this theorem. So we will start from a Frobenius category and Frobenius exact category and kill some of the projective injectives. Yeah, so we take for A, we will take a certain Frobenius exact category and we kill some projective injective module, and the quotient will still be extra-angulated and which will allow us to categorify this ice quiver. Okay, and so the Frobenius category which we choose is simply the category of finite dimensional modules over the pre-projective algebra of type A2. Okay, well, this is a very nice Frobenius exact category which has only finitely many indecomposables, namely the two simple modules and the two indecomposable projectives, and we know all the morphisms between them. They're described by this Auslander-Rayton quiver, where we have to identify this part, this orange line with this orange line. And then you can easily check that in this category, there are exactly two basic cluster tilting objects. Namely, well, we always have to take the two projective injectives, and then we have to take one of the two simples, either S1 or S2. So that gives us these two cluster tilting objects, and they categorify the corresponding ice quivers. And now, well, you see that, well, these ice quivers are not exactly the one we want. Yes, the one we want is even simpler. But we can get this simple one by just deleting one of the projectives. For example, P2. If we delete P2, then we get the ice quiver we're after. Okay, well, and now fortunately, thanks to Nakaoka-Bernoulli's theorem, indeed, if we kill P2 in our category, we still have an extra-angulated category. It now has this Auslander-Rayton quiver, yes, where P2 has disappeared. And well, we still have two basic cluster tilting objects, which are just the images of these two. P1 plus S1 and P1 plus S2. And well, the first one categorifies this quiver, the given ice quiver, and the other one, the same quiver with the opposite orientation. Okay, and now, well, we can generalize. Well, we have the following theorem due to Elin Wu. We take any Jacobi finite ice quiver with potential, and then in analogy with the definition of Frobenius categorification, we always have a stably two-color Frobenius extra-angulated category, the so-called Higgs category. It has a cluster tilting object. Well, we decompose it into a projective part plus the rest. And this pair consisting of the Higgs category and the cluster tilting object categorifies our ice quiver with potential in the sense that we have an isomorphism between the endomorphism algebra of T and the Jacobian algebra of the ice quiver with potential in such a way that the endomorphism algebra of the projective part becomes isomorphic to the boundary algebra inside the Jacobian algebra as the sub-algebra cut out by the frozen idempotent. And, well, there's a link to Amiot's categorification, namely if we take the stable category associated with this Frobenius extra-angulated category, then we find Amiot's cluster category associated with the reduced quiver with potential. Yes, we get the quiver Q bar by removing the frozen part in the quiver Q. We remove frozen matrices and frozen arrows between them, and also non-frozen arrows between them. And then in the potential, we remove all the cycles passing through frozen vertices. Okay, and well, here we have a standard example of this, where this works. Yes, so we take this ice quiver. Yes, and well, you will recognize that this is almost the Auslander-Rayton quiver of the quiver D4. Yes, here we have D4, and then we have 12 vertices corresponding to the 12 indecomposables, and but we have additional arrows, one additional arrow for each Auslander-Rayton sequence. And we get W by from the Auslander-Rayton sequences is by completing their mesh relations. And then, well, there is an associated Higgs category associated with this ice quiver with potential. And it turns out that it is exactly the category of finite dimensional modules over the corresponding pre-projective algebra. Yes, so I have given this example in type D4, but it works for any ADE Dynkin quiver. And these are the motivating examples. So in these motivating examples, the Higgs category is just the category of finite dimensional modules over a pre-projective algebra. And well, it is well known that modules over pre-projective algebras of quivers are the exact analog of Higgs bundles over a curve. Yes, the quiver is of global dimension 1, the curve is of dimension 1, and looking at modules over the pre-projective algebra is the same as looking at Higgs bundles on the curve, and that motivates the name Higgs category. Okay, so this, well, it works very nicely for Jacobi finite ice quivers. On the other hand, yes, we have seen that there are many interesting Jacobi infinite ice quivers. Yes, for example, the ones due to Jensen King Su. Yes, these Grassmannian ice quivers are typical examples of Jacobi infinite ice quivers with potentials, and of course we want to cover these as well. Okay, and that now motivates the third section. Yes, so we want to generalize Elin Wu's theorem from Jacobi finite to Jacobi infinite ice quivers with potentials. Okay, so this is section 3. So we take an ice quiver with potential. We write J for the corresponding Jacobian algebra, B for the boundary algebra. And well, we cannot work in complete generality. We have to make some assumptions if we want to get a nice theorem. So what we, well, the category of finitely generated projectives of the boundary algebra embeds into the category of finitely generated projectives over the Jacobian algebra, just by taking the projective module to the corresponding induced projective module. And the main assumption which we make is that this subcategory is functorially finite in the category of projectives over the Jacobian algebra. Yes, so this is a certain finiteness assumption, yes, which is quite common and which is satisfied in the examples we're interested in particular for the Grassmannian case and for the positroid case. And then we make another assumption. Yes, this assumption makes things nicer. It is not strictly necessary. I will say a word about what happens if we omit it. Now, let's assume it for the moment, because this assumption as well is satisfied for the Grassmannian and the positroid quivers and many others. So we make these two assumptions, and then we have a precise generalization of Eileen Wu's theorem in the Jacobi finite case. Namely, we can find a two-Calabi Frobenius extra-angulated category, still called the Higgs category. We can find the cluster tilting object, and this pair still categorifies the ice quiver with potential. We have the isomorphism between the endomorphism algebra and the Jacobian algebra, which induces an isomorphism between the endomorphism algebra of the projective part with the boundary algebra. And moreover, if we look at the stable category of our Higgs category, then we find the amio cluster category associated with this Jacobi finite quiver with potential. Yes, that's our assumption. This is Jacobi finite, so we have a well-defined Hom-finite amio cluster category. Okay. And yes, so let me, what are the examples? Yes, as I already hinted at, if we take the Grassmannian ice quivers with the canonical potentials, and more generally the positroid ice quivers, then we recover Jensen-King-Su's categorification via Cohen-Macaulay modules, respectively Gorenstein projective modules. Yes, for the positroid ice quivers, we should take Gorenstein projective modules over the boundary algebra. And now, what happens if we remove this finiteness assumption? Well, we can still say quite a few things. So the Higgs category is still well defined, and it is still an extra-angulated category, but in general, we cannot expect it to be a Frobenius category. Nevertheless, it still categorifies in the sense that we have this diagram. And if we quotient by the morphisms factoring through the projective part, well, we don't get the cluster category, but we get Plamondon's subcategory of the cluster category. Yes, for Plamondon in the second part of his thesis has constructed a certain extension closed subcategory of the cluster category, which is now Hom-infinite. So this is Plamondon's subcategory, and Plamondon's subcategory allows to categorify the corresponding cluster algebra without coefficients, and this Higgs category then allows to categorify cluster algebras associated with ice quivers, whose reduction, yes, sorry, I forgot the reduction. So nice. So okay, so then this Higgs category allows us to categorify ice quivers whose non-frozen part is given by Q bar. And I'd like to stop here. Thank you very much for your attention.
Oh, thank you, Bernhard, for your nice talk. Are there any questions?
Yes, for those who came late.
So Bernhard,
Yes.
to already stop your sharing screen? Or?
Yes, just a moment. I will reshare the screen.
Can we have another look at the example of this Grossmania? Yes.